Children, welcome. Work, energy and power. We have already discussed the important concepts, equations and the ideas of this important chapter. Now it's the time to put all of them into problem solving, learn the application skills. So we'll be taking nearly 20 to 25 problems to illustrate the use of the concepts that we have already learned. First example. Force F is equal to 3x square I cap plus 4j cap Newton with x in meter acts on a particle. Work done on the particle as it moves from the coordinates 2 meter, 3 meter to 3 meter, 0 meter is. So he is asking you to calculate the work done by a variable force. And you know that work done by a variable force is given by integral f dot dr. And that can be simplified further. F dot, dr can be written as dxi cap plus dyj cap. So if I substitute for these details, integral 3x square I cap plus 4j cap dot dx I cap plus dyj cap, and from 2, 3 to 3, 0. Let's simplify it further. Integral, and you know that I dot I. What is the value of I dot I? I dot I is I cos 0. Cos 0 is 1. So this is 3x square dx plus 4 dy, and this is from 2, 3 to 3, 0. So if we simplify it, integral 3x square dx is 3 into x cube by 3. So this is x cube plus 4 dy. So 4y, right? And these are from 2, 3, that is 2 to 3, 3 to 0. If you simplify it further, this is 3 cube minus 2 cube plus 4, 0 minus 3. If you simplify it further, it turns out to be how much? This is 3 cube, 27 minus 8 plus 4 into minus 3, that is 27 minus 8 minus 12. So the answer is 7 joules. So the answer for this particular question is 7 joules. C is our correct option. Understand how to work with problems of this kind. Work done by a variable force is given by integral f dot dr. That's the net work done. Example 2. The potential energy of a certain particle is given by half x square minus z square. Then we have to find out the force acting on the particle. So how to find the force acting on the particle? You may wish to recall that the force is given by Fx is equal to minus du divided by dx, and Fy is equal to minus du by dy. In this case, its dependence on y is nil, and Fz is equal to minus du divided by dz. So if we substitute that, minus du by dx, d by dx of u, what is that u? X square minus z square divided by 2. That gives me 1 by 2. Differential of x square is minus 2x. So we are left with minus x. Likewise, Fz is equal to, what is it? D by dx z of course with a negative sign, x square minus z square divided by 2. That further simplifies to plus z. Thus, the force acting on the particle is Fx I cap plus Fyj cap, or we can write as minus xi cap plus zk cap. So So this is the force acting on the particle, minus xi cap plus zk cap. So is A our correct option? Yes. Example 3. A block of mass 10 kg is moving along x-axis, x direction, with a constant speed of 10 meter per second. It is subjected to a retarding force of F is equal to minus 0.1 x Joule per meter during its travel from x is equal to 20 meter to x is equal to 30 meter. Its final kinetic energy is okay. Now he says force is acting and its motion changes from some point to some point and final kinetic energy. And we know from work energy theorem that work done is equal to change in the kinetic energy, final kinetic energy minus initial kinetic energy. And we are supposed to find the final kinetic energy. So final kinetic energy is equal to initial kinetic energy plus work done. What is the initial kinetic energy? The initial kinetic energy is, you can find it out, half mu square plus work done. Can we write it as integral f dx? Yes. So work done is equal to integral f dx. From what value to what value? From 20 to 30. So half mass is 10 into u square is 100 plus integral f. F is nothing but minus 0.1 x into dx from 20 to 30. So this is nothing but 500 plus, and you know this is 0.1 with a negative sign. Integral x dx is x square divided by 2. So I am writing it here 20 to 30, and this becomes how much? You can simplify it further. This becomes 475 joules. So final kinetic energy is equal to 475 joules. So what did we do? We used work energy theorem, according to which the external work done is equal to final kinetic energy minus initial kinetic energy. Remember, one of the very important concepts which is quite useful in handling numerical problems. So 475 joules is our correct option. Example 4. The blades of a windmill sweep out a circle of area A if the wind of density rho flows at a velocity v perpendicular to the circle, then the kinetic energy of the air is okay. So we can show the construction like this. There is a, say, a fan, and the A strikes it perpendicularly like this, and we have to find out the kinetic energy of the air. Now how to do this? Now if I consider the kinetic energy, you know, kinetic energy can be written as half mv square. So we should find out the mass of the air striking. Now how to find out the mass of the air striking? Can we write it as density into volume of the air striking? Yes. So this is half into m is nothing but rho v, right? So rho, volume of the air striking. Now how to find out the volume of the air striking? Now I can write volume is equal to, you know, area into x, right? Volume is equal to area into x. So this is nothing but a into x into, go back, rho v and v square. This is v square. But he says v is the volume of the air striking per unit time. Look at the question. He says sweeps out a circle of area A. So kinetic energy. So now what happens? The volume of the air that swept is AV into T. So what is the mass of the air that is swept? So this becomes into This x can be written as therefore rho a. Now you know this x can be written as velocity into time. So v into t into v square. Rho a vt. So this becomes half rho a v cube into t. So the kinetic energy of the air which is striking is half rho a v cube into t. Remember, t is the time over which the air strikes the windmill blade. So what is our correct option? Half a v cube into rho into t. C is our correct choice. Example 5. A carpet of mass m made of inextensible material is rolled along its length in the form of cylinder of radius r and kept on a rough floor. The decrease in the gravitational potential energy of the system when the carpet is unrolled to a radius r by 2 without sliding is okay. So look at the question carefully. He says carpet of mass m made of an inextensible material is rolled along its length in the form of a cylinder. So this is our cylinder whose radius is r. And when the carpet is unrolled to radius r by 2. So now what do we have? From this we have r by 2. This is the final. So it is unrolled and it becomes something like this. Now he says the decrease in the gravitational potential energy. So decrease in the gravitational potential energy is because of the mass which is unrolled, right? The mass of the carpet unrolled. So what is the mass of the carpet unrolled? So let us find out. Mass of the carpet unrolled is equal to original mass. I can write it as m by pi r square, that is mass per unit area, into area of the remaining or say unrolled part. That becomes m divided by 4. So mass of the carpet unrolled is m divided by 4. Therefore, the decrease in its potential energy is mg into r minus, if I call this as m dash, this becomes m dash g r by 2. This is the initial potential energy. Potential energy is taken with reference to its center. Center of mass is at a distance r initially and at a distance of r by 2 finally. So I will write it as m g r minus m by 2, sorry, m by 4, we calculated as m by 4 into g into r by 2. And how much is it? 7, that is 1 minus 1 by 8, that is 7 by 8 mgr is the loss in its gravitational potential energy. So 7 by 8 mgr is the loss in its gravitational potential energy. 7 by 8 mgr. Example 6. A load hangs from a travelling crane moving horizontally with velocity v. If the load is not to swing more than 4 meters horizontally, when the crane is stopped suddenly, then what is the maximum allowable speed of the crane? This is a simple problem. Try to understand this one. So he says something like this. This is basically a load which initially is kept like this. He says the load should not swing more than 4 meters horizontal. That means if I consider the final configuration, this distance should not be more than 4 meters, or allowable distance is 4 meters. So this is 4 meters and this is 10 meters, this is 10 meters. The question is, what is the maximum allowable speed? Right? This is 4. So now can we find out this distance, that means the rise in this distance or say rise in the position? That is possible. So what is that equal to? So if you look at it, if you look at this triangle, you have this is 10, this is 4. So this becomes root of 100 minus 16, root of 100 minus 16, that's right. 100 minus 16 is 84, so this is root of 84. So this is this distance. Now, if you look at the height by which it rises, so 10 minus root of 84, 10 minus root of 84. So this is the distance by which it can move. Now, I will use conservation of energy. Initial kinetic energy is half mv square and final energy is only in the potential energy form, so mgy. So these two cancel and therefore v square is equal to, what are we going to have? V square is equal to 2gy, or v is equal to root of 2gy. So root of 2, g is 10 and the value of y is obtained earlier. This is 10 minus root of 84, 10 minus root of 84. I want you to simplify this one. So if you simplify it further, so it's not a very difficult task. You know, root of 84 is slightly more than 9. So 9 square is 81. So if you simplify it further, you get the answer as 4.05 meter per second, 4.05 meter per second. So this is our answer as far as the velocity is concerned. So this is the maximum allowable velocity of the crane. A is our correct choice. Example 6. A uniform chain of length L and mass M lying on a smooth table has 1/3 of its length hanging vertically down over the edge of the table. If g is the acceleration due to gravity, the work required to pull the hanging part onto the table is. Okay, so let's show it on the diagram. We have a chain and he says 1/3 is hanging vertically. So L by 3 is here and 2L by 3 is on the table. Work required to pull the hanging part onto the table. Okay. Now I'll take this as the reference level. The work required is equal to change in the potential energy, final potential energy minus initial potential energy. Now if you look at it, this is the initial level for which potential energy is 0. Now if you look at this hanging part, the hanging part which was like this occupies the table. So we need to find the potential energy of this hanging part initially, and of course finally it becomes 0. So this is 0 minus ui or minus ui. Now let us see how to find it out. Minus. Now what is the mass of the hanging part? Isn't it m by 3? Yes. 1/3 is hanging, so its mass must be 1 by 3. And g is the acceleration due to gravity. And where is the center of mass? L by 3 is the length of the hanging part, and therefore half of it corresponds to center of mass. So this is half of L by 3, that is L by 6. Or this is minus L by 6 as I am moving in the downward direction. So this becomes mgl divided by 18. So work done to move it onto the tabletop is mgl divided by 18. mgl divided by 18. So work done is equal to mgl divided by 18. D is our correct choice. Next, example 8. A meter stick pivoted about horizontal axis through its center has a body of mass 2 kg attached to one end and a body of mass 1 kg attached to the other end. The system is released from rest with the stick horizontal. The velocity of either mass as the stick swings through the vertical position is okay. Try to understand this problem clearly. A meter stick pivoted about horizontal axis has a body of mass 2 kg attached to one end and a body of mass 1 kg attached to the other end. So now this is the construction. And you have a mass attached and you have another mass attached over here. This is 1 kg and this is 2 kg. So now from this initial configuration, the final configuration is like this. Velocity is v here, velocity is v, it actually swings like this, right? The heavier part starts falling down and the lighter part starts going up. And this is 0.5 meter, 0.5 meter, these are 0.5 meter because it's a meter stick of length 1 meter. So if you look at it, again I am going to use the idea of conservation of energy. Now what is the initial energy? Initial energy must be equal to final energy. Initial energy is initial potential energy plus initial kinetic energy. This must be final potential energy plus final kinetic energy. That's right? Okay. Now, I am taking this as reference level for which potential energy is 0. So, initial potential energy is 0, initial kinetic energy is 0, final potential energy. The 2 kg block comes down and therefore there is a loss in its potential energy, minus 2 into g into 0.5. Observe what I am writing. There is a loss in its gravitational potential energy because it is coming down. The other is gaining potential energy. Its mass is 1 into g into h plus half mv square for the first particle, and this m is 1 kg and of course velocities are same, plus half m, I will write m1 and m2. m2 is nothing but 2 kg and this is again v square. So if you simplify it further, 0 is equal to minus 2 into 10 into 0.5 plus 1 into 10 into 0.5 plus half into 1 into v square. So half into 2 into v square. This is our expression. By the way, you may pause the video, look at the equation carefully and rewrite them. Okay. Simplify this, you will get v is equal to 1.8 meter per second. Observe that I am not spending a lot of time on the calculations. You need to pause the video, take care of the calculations and proceed. Okay. Our idea is to understand how to put these into applications, not spend a lot of time on the calculations. Calculations are not very difficult. I am trying to skip the calculations here because we can spend little more time on the analysis. So the velocity is 1.8 meter per second. B is our correct choice. Question number 9. A system consists of two identical slabs, each of mass m, linked by a compressed weightless spring of stiffness K as shown. The slabs are also connected by a thread which is burnt at a certain moment. Find at what value of delta x the initial compression of the spring, that is delta x is the initial compression of the spring. The lower slab will bounce up after the thread is burnt through. Okay. So it's something like this. there is a thread and this thread is burnt, and the value of delta x has to be found such that the lower slab will bounce up after the thread is burnt. Okay? So this is the basic idea. Let's see how to do this. So here is the construction. Now I can show this way. This is spring. There is a block of mass m which is kept on the table, and there is one more block, and this is compressed by delta x. This is the initial situation. Now I want the lower block to be lifted. Now if we consider the free body diagram of the lower block, we have mg, right, and we also have kx, correct, and we also have n, but this n becomes 0. Why should it become 0? Because this block lifts up. That means when the block lifts, it loses contact with the ground, and if it loses contact with the ground, the normal reaction becomes 0. So having said that the normal reaction becomes 0, if I consider the free body diagram of the lower block, I can write mg is equal to kx, or x is equal to mg divided by k. So now what should we find out? We should find out the value of delta x. I'll use conservation of energy. What is conservation of energy? The initial energy stored, that is half k delta x square, must be equal to mg into x plus delta x, that's the gain in the potential energy, plus half k x square. This is the final spring energy. So initial spring energy is equal to final spring energy plus gain in the potential energy. We can substitute for that x, of course, here. So half k delta x whole square is equal to mg into x. X is nothing but mg by k, so I can write mg divided by k plus mg into delta x plus half k. Again, x is nothing but mg by k whole square. So further simplification, and delta x turns out to be 3 mg divided by k. So 3 mg divided by k is the expression for the initial compression of the spring. That's right. So the value of delta x is equal to 3 mg divided by k. Okay. Example 10. A body A of mass 1 kg is released from rest on a vertical circular path as shown. If there is a constant resistance of force of 1 Newton along the path, then the speed of the body when it reaches B is okay. So this is the construction. The block is released from this position corresponding to an angle of 60 degree, and the block comes over here, and this corresponds to an angle of 30 degree, and this is A, this is B. The question is, what is the speed of the particle at B? It is released from. Again, we will use work energy theorem, according to which what are all the agencies doing work? Gravity is doing work, so I will write gravity, work done by gravity, and there is a constant force of resistance. So work done by that resistive force, we can call it as friction. That must be equal to final kinetic energy minus initial kinetic energy. Initial kinetic energy is 0, right? So work done by gravity. Now this is the fall in its distance or say position. Now is it possible to find out? Yes. Now observe what we should do. This is 1.6 and this angle is 60 degree. So we can find out this side, correct? This is going to be 1.6 sine 60. This is A. So this distance is going to be 1.6 sine 60. And likewise, can we also find out the position B? Yes, 1.6 and this is meter of course, and this is 30 degree. So this is 1.6 sine 30. 1.6 sine 30. So what is the distance by which it falls? 1.6 sine 60 minus 1.6 sine 30. So m into g into 1.6 sine 60 minus sine 30. That's right. Then plus work done by the friction. Work done by the friction can be found out. Work done, this is a constant force, he says, constant resistance along the path. So we need this distance. This corresponds to an angle of 30 degree. So what is that distance? So we can find out work done is equal to force. Force is 1 Newton. I'll call it as friction into the distance it travels. You know, I'll write here a angle of 2 pi corresponds to a distance of 2 pi r, right? And here 30 degrees, which is basically pi by 6, corresponds to what distance? S. So S is equal to 2 pi r into pi by 6 divided by 2 pi. Is it correct? Yes. So we have pi r divided by 6. So the distance traveled is S. This must be equal to half m Vf square. So now everything is available here for calculation. So you can substitute this being 1 Newton. This is also calculated as here, and you can substitute for these details, and upon simplification you get V is equal to 2.51 meter per second. So the speed of the particle when it reaches the point B is 2.51 meter per second. C is our correct choice. Example 11. A block of mass 5 kg is suspended from the end of a vertical spring which is stretched by 10 cm under the load of the block. The block is given a sharp impulse from the below so that it acquires an upward speed of 2 meter per second. The block will rise to a height. Okay, let's show the construction. Here is the arrangement. A block is suspended from a vertical spring. Now it says under this load it is stretched by 10 centimeter. The block is given a sharp impulse from below such that it acquires a speed of 2 meter per second. The block will rise to what height? Again, energy conservation. You know, initial energy is equal to final energy. Now, this is your initial position, isn't it? And it goes to say this position, this is the final position. And so I'll write initial energy is equal to final energy. Initial energy is in the form of kinetic energy plus spring potential energy, that must be equal to gain in the energy. Potential energy, gravitational potential energy, that's right. So this is nothing but mg into h. The distance by which it moves up is hc plus spring potential energy half k h minus 0.1 whole square, because finally the spring is compressed or elongated by a distance of h minus 0.1. That's right. So we have all the details here. Half m 5 kg, velocity is 2 square plus half k, initial compression is 1 square, and this is equal to mass. What is that mass? Mass is equal to 5 kg into g 10 into h plus half k h minus 0.1 whole square. Correct? Now you may ask, we don't know the value of k, we can find it out easily. Initially mg is equal to kx, that is kx1, as we have noticed this is the value of x1, so we can write x1, and therefore k is equal to x1 divided by mg. So we know the value of k, and that needs to go here, and we can simplify this to get h is equal to 0.2 meters. So it's all about energy conservation, finding the total energy initially and total energy finally. Example 12. The block A has mass m1 and it is attached to a spring of force constant k as shown in the figure. Another block B of mass m2 is pressed against the block A so that the compression in the spring is D. The arrangement is released from rest from this position. The coefficient of friction between the blocks and the ground beneath is mu. The block B will get separated from A if some condition is met. He says block B will get separated from A, which means that both of them will be moving with the same velocity, or we can say the normal reaction between them ceases to exist. Again, the energy conservation of energy can be used here. Observe the diagram here. This is the construction, and of course these two are in contact, m1 and m2. Remember, these two are in contact. I shown them separated. Now if I consider the initial energy, you know, initial energy is nothing but spring potential energy, which is half kd square. And if they acquire same velocity, then I must write work done by the spring, or initial potential energy of the spring, minus the work done by the friction should be greater than 0. That's all. That's right. If this is satisfied, then the block m2 will be traveling faster. They should be equal to or greater than 0, I should say. But in the critical condition, I can say greater than 0. So if m2 should travel faster, or at least with equal velocity, then spring potential energy minus work done by the friction should be greater than 0. Initial spring potential energy is half kd square minus work done against the friction is mu into m1 plus m2 into g, because both the masses are experiencing the friction, into d. D is the distance traveled in spring coming back to its original configuration. So this must be greater than 0, or we write d should be greater than 2 times m1 plus m2 into g into mu whole divided by k. So the separation between these two, or the initial compression of the spring, must be greater than 2 times m1 plus m2 into mu into g divided by k. So B is our correct option. Example 13. Remember, here you will have to go back, pause the video, go back and check for the correct options, check the equations. Okay, you have that liberty, try to understand that. Two identical cylindrical vessels with their bases at the same level each contain a liquid of density rho. The height of the liquid in one vessel is h1 and that in the other vessel is h2. The area of either base is E. If the work done by gravity in equalizing the levels when the two vessels are connected is work done in equalizing the levels. So, we will show the construction. There are two cylinders. Let's assume that there is a stopcock and it says that identical cylinders, that means their cross sectional areas are same. One of them contains a liquid up to height h1 and the other contains a liquid up to height h2, and the stopcock is opened and the levels become same. This is the final level. This is the final level H upon opening. Now the question is, what is the work done by gravity? What is the work done by gravity? Okay. Clearly work done by gravity is equal to final potential energy minus initial potential energy. So let us find out the initial potential energy and final potential energy respectively. Initial potential energy is equal to, we can write it like this. Potential energy can be written as, for example, here, the center of mass of this part is midway between them, the center of mass of this part is midway between them, right? So this must be, how do I write? mgh, correct? Your basic expression is mgh. So how do I write that? Rho, mass is written as rho into A into H1, that's right. This is mass into G into H1 divided by 2. That is the potential energy of this liquid column. Mass into G into H. Mass is volume into density. Volume is AH. Plus rho into A into H2 into G into H2 by 2. What did I write? Potential energy of the next column. So if I simplify it further, I will get Ui is equal to rho G A H1 square plus H2 square divided by 2. That's the initial potential energy. And what is the final potential energy? If I consider final potential energy, this is a liquid column. I consider one cylinder, height is h, the center of mass is here. So this must be again mgh, density into A into h, that's mass, into G, center of mass is at a height of h by 2. And this is for one column. There are two columns into 2. So what do you have? This is nothing but rho G H square into A. 2 and 2 cancel. Rho G H square into A. Where, what is this height? This height is nothing but H1 plus H2 divided by 2. Is that correct? Yes. So this is rho A G H1 plus H2 divided by 2 whole square. This is my equation number 2. So work done is equal to final potential energy minus initial potential energy, that is rho Ag into H1 plus H2 divided by 2 whole square minus, what is the initial potential energy? Rho Ag into H1 square plus H2 square by 2. So go back to this one. This is your initial potential energy. This is the final potential energy. So work done is the difference between them. and I want you to try this simplification. It's not a difficult one, it is a simple calculation. It becomes 1 by 4 h1 minus h2 whole square into g into a into rho. So work done is basically the change in the potential energy of the system. It's the change in the potential energy of the system. All right. So 1 by 4 h1 minus h2 whole square a rho g. That's our correct option. Example 14. An object is attached to a vertical spring and is slowly lowered to its equilibrium position. This stretches the spring by x. If the same object is attached to same vertical spring but permitted to fall suddenly, the spring stretches by. Okay. Read the problem carefully. An object is attached to a vertical spring and is slowly lowered to its equilibrium position. So finally, it is in the equilibrium position. So because of this, x is the elongation of the spring. However, if I consider it like this, it is attached and is released. Now by what distance does it fall? So I'll call this as some x dash. What's the value of x dash is the question. Now this has already come to the equilibrium position, so I'm going to write in the equilibrium position. Remember, there is no velocity, so I'm going to write mg is equal to kx. So x is equal to mg divided by k. Mg by k, that's my equation number 1. Whereas for this configuration, I'll say initial energy is equal to final energy. Initial energy, what is initial energy? It is mg x dash. Mg x dash. That's right. So what do I have? I have this is equal to half k x dash square. That's the final energy. So half k x dash square is equal to mgx. That gives me x dash is equal to 2mg divided by k. X dash is equal to 2mg divided by k. So this is equation 2. So now equation 2 divided by equation 1 gives me x dash divided by x is equal to, what is it? 2, or x dash is equal to 2x. So the spring stretches by a distance 2x when it is allowed to fall suddenly. C is the correct option. Question number 15. An engine is hauling a train of mass m on a level track at a constant speed of v. The resistance due to friction is F. What extra power must the engine develop to maintain the speed up to a gradient of h in S? Remember, h in S represents sin theta. So it implies h divided by s. Remember this convention. So if I say h in s, it implies sin theta is equal to h by s. So now the extra power it requires is equal to F into v, force into velocity. That's right. So now force is equal to mg into sin theta into v. That's right. Because now it is on a track, sin theta, theta is this angle, and clearly this is mg sin theta. So this mg sin theta into v must bring me velocity, power, mg h divided by s into v. So mg hv divided by s is our correct option. A simple example 16. The potential energy between two atoms in a molecule is given by u is equal to a by x to the power 12 minus b by x to the power 6. A and b are constants, x is the separation. The atom is in stable equilibrium position when we had learned that stable equilibrium corresponds to u and f related by f is equal to minus du by dx and f is equal to 0. So I am going to differentiate this u is a by x to the power 12 minus b by x to the power 6. So if I simplify it further, I will get minus 12a x to the power of minus 13 minus 6 b x to the power minus 7 is equal to 0, and you can simplify it further to get x is equal to 2a by b to the power of 1 by 6. So x is equal to 6th root of 2a divided by b. D is our correct choice. 17. The block of mass m moving on the frictionless horizontal surface collides with a spring of spring constant k and compresses it by length L. The maximum momentum of the block after collision is, okay. The question is maximum momentum. Now, momentum is mv. So, using energy conservation principle, I can find out velocity and I can calculate momentum. Okay, let us see how to do this. So, clearly its kinetic energy is given by half mv square, and that must be equal to half k L square, right? Maximum momentum corresponds to maximum compression. Maximum compression refers to L. So this gives us V is equal to root of, or say k L square divided by m under root, or it simplifies to L root of k by m, and momentum P is equal to m into V. So we can write m into L root of k by m, and I can take that m inside and it becomes L root m into k. So momentum is equal to root of km into L, that is root mk into L. D is our correct choice. Next one, a particle gets displaced by delta r is equal to 2i plus 3j plus 4k cap under the action of a force 7i plus 4j plus 3k. The change in the kinetic energy is equal to, simple problem. According to work energy theorem, change in kinetic energy is equal to work done. So what is that work done equal to? Work done is given by F dot ds, or say F dot r, right? So F, what is that F? 7i plus 4j plus 3k dot displacement is 2i plus 3j plus 4k. So if I simplify it further, I get 7 into 2, that becomes 14, plus 4 into 3, 12, plus 3 into 4, 12. So how much is that? That becomes 38 joules. Simple problem. Change in kinetic energy is equal to work done. Work done is F dot R. So 38 joule is our choice. A is our correct option. 19. A moving particle of mass m makes a head-on collision with another particle of mass 2m, which is initially at rest. The percentage loss in energy of the colliding particle on collision is close to. Here he is referring to the kinetic energy, of course. And we can directly use the formula. The fractional loss in kinetic energy is equal to 1 minus m2 minus m1 divided by m2 plus m1 whole square. That becomes 1 minus m2 and m1. So I can write it as 2 minus 1 whole divided by 2 plus 1 whole square. 1 minus, this is 1 by 3 whole square, 1 by 9, and this becomes 8 by 9, right? And this is fractional change, and therefore percentage change is delta k by k into 100, that is 8 by 9 into 100, right? So 800 divided by 9, which is close to how much? 90%. So 90% is the change in kinetic energy, percentage change in kinetic energy. C is the correct choice. 20. Two springs of force constants 300 Newton per meter and 400 Newton per meter are joined together in series. The combination is compressed by 8.75 centimeter. The ratio of energy stored in A and B is EA by EB, which is equal to. So there are two springs which are connected in series like this. This is KA, this is KB, and the combination is compressed by 8.75 centimeter. Now when the spring is compressed by certain distance, let us consider it like this. Let's assume that A is compressed by a distance x. So clearly B is compressed by 8.75 centimeter minus x, because the total compression is 8.75. So if this gets compressed by x, the other gets compressed by 8.75 minus x. Now we know that it's the same force because they are connected in series. So you can write K1 x1 is equal to K2 x2. What is K1? Ka. X1 x, K2 kb into 8.75 minus x. So do we know the values? Yes, 300 into x is equal to 400 into 8.75 minus x. That gives us x is equal to, you can simplify it further, x is equal to 5 centimeter. So once I get the value of x, how do I proceed? The energy. To get the energy, I also need the value of xb, which is 8.75 minus 5, which is 3.75 centimeter. Now energy of A divided by energy of B is half KAXA square by half KBXB square. K is 300, XA is 5 square divided by 400, 3.75 square. So you can simplify it further and it reduces to 4 divided by 3. So it simplifies to 4 divided by 3. So A is our correct choice. Next one. A 70 kg man leaps vertically into air from a crouching position. To take the leap, the man pushes the ground with a constant force F to raise himself. The center of gravity rises by 0.5 meter before he leaps. After the leap, the center of gravity rises by another 1 meter. The maximum power delivered by the muscles is. Let us see. Now, if you consider the power dissipated, how to find out the power dissipated? The power dissipated is work done divided by time. Work done is nothing but increase in its potential energy, so I will write it as mgh. What is that? M 70, G I will take 10, H 1.5. How is it 1.5? The center of gravity rises by 0.5 meter before he leaps, and after he leaps the center of gravity rises by another 1 meter. That's right. So this is equal to the work done, which can be simplified 1.5 into 7, that is 105 into 10 into 10. So we have 1050 joules. And we also need time. How to do that? Simple. This can be calculated using your simple equation of motion, S is equal to ut plus half gt square. That gives us t is equal to root of 2 s divided by g. The value of s is nothing but 1 meter, so divided by 10, and that gives you t is equal to root of 0.1, which further reduces to 0.316 seconds. So upon simplification we get power dissipated as work done divided by time. Work done is 1050 divided by the time taken is 0.316, and it reduces to 3.3 into 10 to the power of 3. So during the takeoff, the power dissipated is 3.3 into 10 to the power of 3 joule per second, that is watt. So 3.3 into 10 to the power of 3 watts at the takeoff. So during takeoff, this is 3.3 into 10 to the power of 3. 22. A wind powered generator converts wind energy into electrical energy. Assume that the generator converts a fixed fraction of the wind energy intercepted by its blades into electrical energy. For wind speed v, the electrical power output will be most likely proportional to. Okay. Remember, we had come across with a problem of this kind. The power is nothing but work done divided by time. Work done is nothing but change in kinetic energy. Change in kinetic energy is nothing but final kinetic energy minus initial. Remember, we had come across this kinetic energy, which is given by half rho a v cube. Remember, half rho a v cube, and this is divided by t. So if you simplify it further, we get power is directly proportional to v cube. A very simple problem. Power is directly proportional to v cube. C is our correct choice. Next, a block of mass 0.1 kg is connected to a spring of unknown spring constant. It is compressed to a distance x from its equilibrium position and released from rest after approaching half the distance, that is x by 2, from equilibrium position. It hits another block and comes to rest momentarily while the other block moves with a velocity of 3 meters per second. The total initial energy of the spring is, it says, a block is connected to a spring, is compressed to a distance x from the equilibrium position and released. After approaching half the distance from equilibrium position, it hits another block and comes to rest momentarily while the other block moves with a velocity of 3 meters per second. Right. So clearly, in such problems, the idea of conservation of momentum and conservation of energy are useful. So if you look at the conservation of momentum, we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. So what are these things? What is the value of m? m1 0.1. What is its initial velocity? Don't know, we have to find out. m2 is m into 0. This is equal to, he says, it comes to rest momentarily, so I'll write 0.1 into 0 plus m into 3. So we have the relation between them. 0.1 u is equal to 3m. 0.1 u is equal to 3m. Now, we can also make use of the energy conservation. Half mu square should be equal to half mv square. Right? Half mu square is equal to half mv square. So how do we find it out? Now we know that half 0.1 u square is equal to half m. This is 3 square. So upon simplification we get u is equal to, we know the value of u and m are related by this equation. So I can say m is equal to 0.1 divided by u. This gives me m is equal to 0.1 u divided by 3. That is right. So you can go here and it gives us u is equal to 3. Now the total initial energy of the spring. So total energy of the spring initially is equal to half k square, which is nothing but half mv square. So because the total energy is conserved, I can say half mv square, half mu square gives us the energy, and we know this value half, this is 0.1, and we have calculated the value of u, and the value of u turned out to be 3. So how much is that? So it becomes 0.6 joules. 0.6 joules. Next one. A block of mass m is equal to 2 kg is connected to a spring of force constant 50 Newton per meter. Initially the block is at rest and the spring has natural length. A constant force of 60 Newton is applied horizontally towards right. The maximum speed of the block is, okay. So you are applying a constant force of 60 Newton along this direction and the spring is in its natural length. Initially the block is at rest, of course. Now, when this force is applied, when a constant force is applied, there is an elongation. What is that elongation equal to? This is given by F divided by K. What is that? 60 divided by 50, that is 1.2 meter, or 6 divided by 5, 1.2 meters, 6 divided by 5. Now we can use the conservation of energy. What does that give us? The total initial spring energy is equal to final energy kinetic, which is kinetic energy. That is right. So we have to find out the maximum speed of the block. We need the value of this one. So what is that? Half k x naught square. Do we know this one? So we can simplify this one directly. We can write v naught therefore is equal to, half and half cancel here, these two cancel, and v naught is equal to x naught root of k by m. So x naught root of k divided by m, and we have found the value of x naught, which is 6 by 5. K is known to us. What is the value of k? K is 50. The mass of the block is 2. So if I simplify it further, 25, 5 and 5 cancel, and this gives us 6 meter per second. So the velocity, the maximum speed of the block turns out to be 6 meter per second. So this should be meter per second. So the maximum speed of the block is 6 meter per second. water through a well is lifted through 10 meter and delivered with a velocity of 10 meter per second. If 10 liter of water per second is supplied, the power in kilowatt of the motor is. Okay. We can again make use of energy conservation here. Water is lifted and it is delivered with a velocity. So, work is done to provide kinetic energy and to lift it. Work is done to provide kinetic energy and to lift it. What is that kinetic energy? It is half mv square. And this is mg into h. And power delivered is work done divided by time. So, I am going to write 1 by t, half mv square plus mg h. We can simplify it further. This becomes m, I can take t outside, we are left with v square by 2 plus gh. Mass is known to us 10 and this is 1 second per second of course into v square divided by 2, 10 square divided by 2 plus 10 into h. The what is this one lifted through 10 meter. So, if I simplify this 50, 150 and 150 into 10, 1500 watt. So, 1500 watt is the power. So, the power required is 1.5, that is 1500 watt, which actually corresponds to 1.5 kilowatt. So, 1.5 kilowatt is the answer for this one. B is our correct choice. Well, with this problem we have come to the end of this session, but please go through all these problems one more time. Remember the basic ideas. Most of the times we use energy conservation, work energy theorem in solving the problems here. Sometimes you may also notice the usage of momentum conservation to arrive at the required answer. So, the key ideas are very simple. Usage of work energy theorem, usage of conservation of mechanical energy and the usage of momentum conservation. All the best. Thank you very much.